Yesterday we were talking about the phase lock loop and we analyzed it, and what we found was that the gain of the phase detector times the gain of the VCO needs to be high to support a wide lock range, but needs to be low to have a small amount of phase error in the output. Okay. Essentially, the VCO gets modulated by the reference frequency, that is known as reference feed through. So this is the phenomenon where VCO gets modulated by FF. Ideally, you would like an arrangement where the control voltage of the VCO is such that you get the desired frequency. Now, in addition to the DC value that corresponds to the output frequency, you have some time variations in the control voltage, which gives you frequency modulation. Okay, that's what we saw. And this gives you sidebands. If the modulation is weak, if the modulating signal is small, you get just 2 sidebands around the carrier. And to reduce this, reduce the reference feed through, KVCO times KPD has to be low. Now, we also later saw that for the lock range, we need to have KPD times KVCO high at DC. Okay. I mean, we have taken a case where KVCO and KPDs happen to be constant over all frequencies, but what is relevant for the lock range is the DC values of, or the DC values of KPD and KVCO. Is this clear? Or no? Is it okay or no? So, the control voltage of the VCO needs to be some DC value. So, the input, the phase detector input has to be some DC phase, meaning a constant phase shift over all time. Okay, that's what is meant by DC when we talk about phase. That means that the phase difference between the inputs is not changing. So that if you have a large value of KPD, then you can have a small value of phase difference which supports a given value of control voltage. Okay. So how would we do this? The loop in the phase model, the loop looks like this. KPD, there is one integrator in the loop. This is the model of the phase lock loop in terms of the input and output phases in the frequency domain. What do we need to do to widen the lock range? Should be high, but we saw that if we just make it high at all frequencies, we have a problem with reference feed through, right? Because the reference feed through feeds at the same point as pi n. So what do we have to do? What if the reference feed through has some transfer function to the output, that is this E of t, or in this case E of s, there is some transfer function between E and phi out. To minimize that, what is the frequency at which we should look at the transfer function? What is the relevant frequency for reference feed through? FRF, right? FRF and its harmonic. So, although we said KPD times KVCO needs to be high at DC for lock range and low for reference feed through, we are really talking about different frequencies. The reference feed through refers to the transfer function of the filter, transfer function of this system at FRF and its harmonics, and the lock range is dependent on the value of KPD and KVCO at very low frequencies. Okay. So, is there some way to break this deadlock?
So, you have KPD to be high,
yeah.
Put some kind of filter in.
KPD to be high and put some kind of filter in between. So, essentially this KPD should not be constant. Let's say it is some, instead of a constant we express it by a transfer function. So, you are saying the transfer function should be like what? So, it should be like this. Should it be first order, second order, what would you start with? Huh? Higher the order the better. Okay, let's see. So, let's start with first order. So, the first thing is once we recognize that we are talking about 2 different frequencies for this trade-off, for 2 different frequencies at which the values of KPD and KVC are relevant for lock range and for reference feed through. We can make it high at low frequencies where we want it to be high and low at high frequencies. So that means that the phase detector itself or something else in the loop should behave like a low pass filter, which makes the phase detector have a large gain at DC and small gain at high frequencies. Okay. So let's just take the transfer function to be some first order transfer function, or let's what is the, I can go on doing this, right? So this is a low pass filter. I can increase the DC gain even higher. So I can start with this, but then make it higher and higher gains. What do I get in the limit if I keep on doing this? I get an integrator which has infinite DC gain, but low gain at high frequencies. So let's say I will just start off with something like that. Okay. So I'll say the phase detector transfer function is some KPDI by S. That subscript I indicates that it's an integrating transfer function. Okay. So if we have this, right? We also have, of course, 1 over n. So this is the loop we have. If we replace a phase detector with a constant gain with a phase detector which has which behaves like an integrator. Okay. Now because it's an integrator, it has infinite gain at DC, so it can support a control voltage at its output with 0 input, right? An integrator can do that. An integrator's output can be non-zero with a 0 input. Okay. So will this work? This is unstable. Why? So both there are 2 integrators in a loop and it is unstable. Okay. So how will we deal with that?
You can make that KPD by S plus.
KPD by S plus something. Let's see if that works. So instead of this, we'll say that instead of a pure integrator, we will make it some omega PD. Okay. Clearly, omega PD has to be small because we'll have a high Q. Let's study that. Okay. Are you all familiar with stability analysis? What kind of how would you assess a system stability? And you see the phase margin. Anything else? That I've forgotten myself, but I think you need to know the polynomial to do that, right? Approximated by a second order system. How will you do that? Yeah. First of all, we only have a second order system, so we don't have to do much here. But yeah, maybe some terms are negligible in some cases. What else? Root locus. So some things like that. There are many techniques for evaluating stability. So if you are sufficiently familiar with it, I can go quickly through this. So the transfer function of a feedback system. So let's say we have a certain loop gain L and we have unity feedback around it. So the loop gain of the loop is L. Okay. What is the transfer function of this? So the transfer function is L of S by 1 plus L of S. So instability means that 1 plus L has roots on the imaginary axis or in the right half plane. Okay. And the same thing is expressed using phase approximate criteria like phase margin and gain margin, etc. So in this particular case, loop gain is 1 by n. Okay. So what do we get? 1 plus L of S will be divided by something. It will be, this is 1 plus L. So basically this is what appears in the denominator. This is what appears as the denominator polynomial of the closed loop system. Okay. So for a second order case, we can simply, it is, both the coefficients are, all coefficients are positive. So it is stable, but in a second order case, if you have such a condition, it is stable. But what is of interest is also not whether it is just stable or not, but also how close it is to instability, right? And that is characterized by the quality factor of the system. So, if you have a very high quality factor, there will be a lot of ringing. That means a small disturbance will induce disturbances in the system that last a very long time. That is also a kind of instability. I mean, it's not unstable, but it is close to being unstable. So, the denominator polynomial for this system this much. So, what is the quality factor and what is the natural frequency? I mean, the second order system can be characterized by the natural frequency and quality factor. What is the natural frequency? So, if you have a square plus bs plus c, the natural frequency is square root c by a, and the quality factor omega p is, and the quality factor is root ac, yeah. So, it is this, and you just okay. So, what does this say about making it a low pass filter? So, the idea here was we will make KPD large and omega PD low, so that the gain at high frequencies is small, right? That was what we were doing. Okay. So, as we go on doing that, we get higher and higher values of the quality factor. Okay. So, we can't do this because, yeah, that's true. This will give a large value of KPD at DC, but it renders the system almost unstable. So, the idea was good of trying to make KPD high at low frequencies and letting it roll off at high frequencies. But the problem is it becomes a very high Q system and we can't do this. Okay. So, what do we do next? No, N is given by the system, so you don't have freedom to play with N, right? You have to generate a certain output frequency from a certain input frequency. So, N is given to you, and making N large doesn't help also, because, yeah, anyway, you can't play with N. So, huh? Will it become more unstable or less unstable? Okay. So, let's there are many ways of assessing stability. So, let's just look at some approximate way of assessing stability using Bode plots and see what we can do. Okay. So, let's consider firstly, I think all of you know what Bode plots are, and these are most useful for systems which have real poles and real zeros, right? If you have complex poles, you can't use Bode plots very well because you can have resonances which you can represent on the Bode plot. Bode plot consists of straight line segment approximations to the actual frequency response. So, if your response contains, let's say, number of real zeros and poles. So, let's say this is your system, and Z1 is smaller than Z2 and P1 smaller than P2, smaller than P3 and so on. And there is some multiplier H0, which is the DC value. So, you start from the DC value, and if you hit a pole, then the slope of the magnitude of response changes by minus 20 dB per decade. If you hit a 0, when I say hit a 0, I mean as you increase the frequencies, if you reach the frequency of a 0, then the slope increases by plus 20 dB per decade. Okay. So, let's say this is P1 and this is P2. So, the slope increases. Here it is minus 20, here it is minus 40, and let's say you hit a 0, you go back to minus 20, that is the 0 increases the slope by plus 20 dB per decade, and perhaps you have P3 here and Z2 there. Okay. this is the magnitude response, and the phase response. How do you plot the phase response? At the value of the pole, you will have an excess phase shift of 45 degrees. Below the pole, it will be 0. Above the pole, it will be 90. So, phase lag of 45 degrees. In case of 0, it's a phase lead of 45 degrees. Let's assume that the poles are far away that you can do this, but that may not always be the case. So, roughly speaking, you also can draw the phase response. So, this is minus pi by 4 and so on. Okay. Now, because of the 0, you have a phase lead. So, it will tend to go back and then come back to this one. Okay. So, if the poles and zeros are close together, it won't reach either minus 90 degrees or plus 90 degrees. Okay. So, let's assume that it goes to minus pi by 2 and then reaches minus pi and comes back to plus and then goes back and comes back to this. Okay. So, this minus pi by 2 is because of the first pole. This minus pi is because of the second pole. Now, this is minus pi by 2 because of the 2 poles and 0. 0 has cancelled the phase lag of the pole. This minus pi is because of 3 poles and 1 0, and this is because of 3 poles and 2 zeros. Okay. Now, what is the idea behind this phase margin? So, at unity gain, the phase margin phase lag should be less than pi. Okay. So, in this case, let's say the poles and zeros are well separated. The phase margin is only an approximate kind of criterion, right? So, let's say the poles and zeros are well spread out. Okay. So, this is the unity gain frequency. So, in this particular example, the phase lag is almost pi. Okay. Now, we say that the phase lag has to be less than pi to have good margin for stability. Okay. So, what can you say about the number of poles and zeros before the unity gain crossing? Can I have any number, but is there a relationship? Pole minus 0 should be 1, right? Because if you have 2 poles, I mean the total, let's say the poles are well separated before, so each pole gives you a phase lag of pi by 2, each 0 gives you a phase lead of pi by 2. Okay. Now, if the number of poles is more than the number of zeros by 2, you get a phase lag of pi, right? So, it has to be only 1. So, you can have many poles and zeros, but the number of poles can be greater than the number of zeros by 1. That's all. Okay. Is this clear? So, this is some approximate criterion of stability that before in some cases, yeah, when you have right half plane zeros and so on, you can't have this. Okay, by the way, all this is for when the poles and zeros are in the left half plane. Okay, when you have right half plane zeros, it will increase the magnitude response by plus 20 dB per decade, but it actually provides a phase lag. So, that it doesn't apply here. Okay, because of the phase lag, you can have instability, and it may not have reached the magnitude crossing. Okay. So, when we say number of poles minus zeros, we assume that all poles and zeros are in the left half plane, then you can play this, and of course, the poles are real, poles and zeros are real. Okay. So, it is an approximation of that. That is the exact criterion, that the roots of 1 plus L should be in the left half plane. That is the criterion for stability. There are many approximate things that we use which hold under restricted conditions. Usually, the problem is the conditions are not stated, but in this case, yeah, this is true only if the poles and zeros are both in the left half plane. Okay. So, you can have many poles and zeros, but the number of poles minus the number of zeros can be 1. Okay. It can't be more than 1. If it's more than 1, you will reach a phase of 180 degrees, and it may become close to instability. So, phase margin is again an approximate criterion. The only thing it says is if you provide, let's say the phase margin is a certain amount PM. If you have an additional phase shift of PM in the loop, it will become unstable. So you can't necessarily say that it is unstable because of a certain phase margin or something like that. Okay. So in this case, it is this is true that if you have poles and zeros in the left half plane, then if the number of poles minus number of zeros before the unity gain frequency is 1, it will be stable. Okay. Now again, we are talking about real poles and well separated poles and zeros, etc., etc. So if the number of poles minus number of zeros before the unity gain frequency is 1, what is the slope at zero crossing? Minus 20 dB per decade. Okay. So there is an approximate way of assessing stability just by looking at the magnitude plot of the loop gain. So it says that at unity gain crossing, the slope of the magnitude response should be 20 dB per decade. Okay. It should look like a first order system around the unity gain frequency. If it does that, it is a stable system. Like many things could have happened before.
This magnitude response,
Yeah.
even it crosses the number of pole minus number of zero equal to 1 before the unity gain frequency.
Yeah.
Let's say it can have some before unity gain frequency, the phase margin phase can also go to minus pi.
Yeah.
Frequency.
Yeah.
At that point, since the gain in the magnitude is more than 1,
Yeah.
the pole can go to right after. Like
No, it won't. So you can have a system like. So anyway, let's take a system where, so let's say it is of the type like this, right? So it starts off with minus 60 dB per decade, okay, and it shifts to, it has two identical zeros, so it shifts to minus 20 dB per decade. And if you plot the phase plot, it starts from minus 3 pi by 2, minus 270 degrees, and then it reaches minus pi by 2. Okay, this is a stable system. Although there is a point where the phase shift is minus pi and the gain is 1. So let's say this is some k times this. So this is a stable system. Okay, is this clear? I mean, like sometimes the intuition for negative feedback is given that you apply some signal and some signal comes back and then it gets added either in phase or out of phase. But in all those descriptions, you implicitly assume a delay. Whenever, I mean, even in the semantics, right? When you say then something comes back, you assume some kind of delay, extra delay beyond what is here. So if this is minus pi and if this is more than 1, the feeling is that, oh, it is adding in phase and it's more than magnitude, so it will become unstable. No, it doesn't. So the gain will be, so let's say this magnitude is 4, okay. So the loop gain here is minus 4, okay. The gain will be L over 1 plus L. So that's what happens, okay. Huh? What was that? Oh, the question was if you have, let's say you have 20 dB per decade cross slope at the zero crossing, at the unity gain crossing, but you have many poles and zeros before that, okay. It is possible to have a phase shift of pi, but a gain of more than 1. Okay. So is that a stable system? The answer is it is a stable system. Okay. Is this part clear? So you can have gain more than 1 and phase shift of pi. So although it looks like the feedback is adding up in phase and larger in magnitude, it doesn't blow up or anything. So this happens particularly with conditionally stable systems, all these things will happen. So if you plot the root locus of this, if you reduce the value of k, it can become unstable. Okay. So if I shift it like this, reduce the value of k meaning I shift the entire magnitude plot downwards, right. If I do this, this is an unstable system. Okay. So there are systems in which if you, I mean normally, so this kind of phase margin was useful, especially in the beginning of negative feedback, because you had only some kind of simple systems and this conditional stability was not very well understood, right. So there, I mean, as you went on increasing the gain inside the loop, it would be stable for some values of gain and it would become unstable. But you have conditionally stable systems where for very small values of gain, I mean for k equal to 0, which means there is no negative feedback loop, obviously it is stable. And as you increase the value of the gain, this is what you do in root locus, right? You have some gain factor and you keep on increasing it and plot the locus of the loci of the roots. So you can have the roots go into the right half plane, then for higher values of gain, it can come back into the left half plane and so on. So you might have seen root loci which are like this. Okay. So as you increase the values of the gain, it can come back. So if your system is operating somewhere here, then you can have frequencies where the phase shift is pi, the gain is more than 1, but it is a stable system. Okay. The ultimate test of stability is whether the poles are in the right or left half plane. It's hard to evaluate it, especially when you don't know the analytical description of the system. That's why we have all these other approximate criteria which you can evaluate from simulation, like the magnitude plot or the phase plot. Okay. But for the purposes of analyzing the PLL, it's enough to know this one approximate criteria, that if the slope of the magnitude response is minus 20 dB per decade at the unity gain crossing, then it is a stable system. Okay. Is that okay? So what we had was, so originally we had the loop gain to be KPD times KVCO by S times 1 over N. Okay. What does that look like? It has some, it has a minus 20 dB per decade slope throughout. Okay. And what is this frequency? So this is the unity gain frequency, which is KPD KVCO by N. What I am plotting here is the magnitude of the loop gain versus the frequency. Then we said this is not sufficient for us, so we went to something like, we made the phase detector into an integrator. Okay. So what is the loop gain in that case? It may be something like this. Okay. What is this frequency? It is this, and this is clearly unstable according to the criteria we just stated, that the magnitude response has a slope of minus 40 dB per decade at the unity gain crossing. Okay. So this will give you a very high gain at DC. Okay. This extra infinite gain at DC is what we were looking for to increase the lock range, but it doesn't work. So, and it also gives you high attenuation at high frequencies, but again there is a problem. Okay. This is unstable, and if you make it something like KPD by 1 plus S by omega PD, KVCO by S 1 over N. So this is a large KPD. I mean, I am just saying large to distinguish from this value of KPD. Okay. Then the response will look something like, so it will follow first order and then second order, right? That's what something like this does, and this is also unstable. So both these are unstable. Again, applying the criterion of what is the slope at unity gain crossing, we can see that it is unstable. So I brought about this criterion because then we can see what to do to make this stable. What can we do? So we have to have a 0 before the unity gain crossing. Okay. So we need to make the magnitude response. So maybe this corresponds to the second one. Okay. And this is unstable. So what we do is we have a 0 before this, so that it shifts to something like this, and we can have many poles after that also. Okay. Then it doesn't matter, right? So we can have 1 or even 2 poles beyond the unity gain frequency. You can think of either stabilizing the second one or increasing the gain of the first one. So this is the first one. okay, at DC and frequencies below the unity gain frequency, but you don't meddle around with it at the unity gain frequency. Okay. So this is how you have to modify it. So let me draw a cleaner plot. So original loop gain plot was like this. This corresponds to KPD, KVCO by S. Now this is inadequate for lock range because the DC loop gain is not enough. So we say even we make the DC loop gain infinity, right? I mean we make the phase detector look like an integrator at very low frequencies, okay? But we come back to this at a particular frequency of the 0, okay? So we do this because we do this part because we know that this extra loop gain will give us a large lock range. We do this because it is a stable system. We need this for stability. And then let us say our omega ref is here. We need a large attenuation at omega ref. So we can of course continue along this, or we can even further attenuate those components by doing this. Okay. Why does it get attenuated if we do this? This is the loop gain plot. What we are interested in is the closed loop gain. Why did I say that we can attenuate the loop gain at high frequencies? So this part is fine. We had to increase the loop gain, but the transfer function of the disturbance to the output phase is a closed loop quantity. Here this is the loop gain. How is it related to this? Yeah. So the closed loop gain of a feedback system is of the form H ideal, where H ideal is the transfer function with infinite loop gain, right, times L over 1 plus L. Okay. So in the range of frequencies where the magnitude of the loop gain is much more than 1, the gain is approximately the ideal transfer function that you want. The transfer function is approximately the ideal value, okay. And where the magnitude of the loop gain is much less than 1, it is the ideal gain times L, okay. So when the loop gain drops below unity, the loop gain appears directly in the expression of the overall transfer function, okay. So essentially if this is the loop gain, below this point, if it's a unity gain feedback loop, the gain will be unity, and above this it will simply follow this curve, okay. So if this was an unity gain feedback, the gain would look like this, the closed loop gain would look like this. So again, using the loop gain you can plot the closed loop gain, okay. Now you want attenuation in the closed loop response, so you introduce attenuation poles beyond the unity gain frequency in the loop gain. So this now gets us the best of both worlds, that we have an integrator for the phase detector. So that means that we really have an infinite lock range. We will see that in a moment. And we can also introduce further attenuation poles between the unity loop gain frequency and the reference frequency, okay. That will further increase the attenuation for the reference feed through, okay. So we can clean up our phase, the output phase, as well as increase the lock range. So this is the classic PLL that is used. This is the practical PLL that's used. So that the other first order PLL is not a very practical case because there is a severe trade-off between the lock range and the reference feed through, okay. And that had one integrator in the loop. Here we are talking about the phase domain model. So in that case, there is an integrator which is integrator because of the VCO. VCO integrates the control voltage to give you output phase. So if you have one integrator in the loop, it's known as a type 1 loop. I think you would know this from control systems. And if you have two integrators in the loop like we do have now, it is known as a type 2 loop, okay. So what is the distinguishing characteristics of these, like in the control system parlance? What is it? Have you heard of type 1 type loops? No? Okay, what is a type 1 loop? What does it do for you? What does a type 2 loop do for you? So type 1 loop with an integrator, it's supposed to follow a step response with 0 steady state error, right? Similarly, type 2 loop will follow a ramp response with 0 steady state error, and type 3 will follow the next one, and so on. Okay. So in this case, we have a type 2 loop. This is the practical loop that is used for a phase lock loop. Okay. So this original expression was KPD KVCO by S. Okay. How do we realize this? Realize this red curve. What is the transfer function of that? Yeah, so easiest way out to think about it is, we said that we wanted an integral control. So, okay, so let's say this red part here corresponds to having an integrating phase detector and the VCO, okay, and this blue part corresponds to having a what is known as a proportional phase detector, because the output is simply proportional to the input, and the VCO, okay. What is the composite response? So if we did this, it would be unstable, okay. This is KPDI by S, KVCO by S. This is KPD times KVCO by S. This is stable, but not good enough for lock rings. What we want is this. So what is the equation that describes this? Sum of the two, right? This is the Bode plot. So the sum of the two is simply the larger of the two. So we want to follow this integrating curve up to this and the proportional curve up to this. Okay. So what we really want is KPDI by S plus KPD times KVCO by S. Actually, I forgot the N everywhere. Okay. And what is the condition on KPDI? What is this frequency? Huh? What is? No, not omega f. What is this? This should be, this is KPD KVCO by N, right? What is this frequency? KPDI by KPD. This is the frequency of the 0. Now, you introduce an integrating phase detector part, and this KPDI should be such that KPDI by KPD is less than this whole thing. Okay. Okay. And this in turn should be less than omega f. Actually, I think I have been a little sloppy with the notation. So this should, in terms of omega, all of this should have been 2 pi KVCO, right? So, okay. So these are the conditions. So this first condition ensures that it is stable, that the slope is 20 dB per decade at the 0 crossing magnitude, 0 dB crossing. And the second condition ensures that there is high attenuation for the reference feed through. And you can have additional poles here. So let me call it like P2. Okay, let's say you have one additional pole, in which case you should have this to be less than P2, P2 should be beyond the unity gain frequency to ensure stability. Okay, if P2 comes too close to unity gain frequency, again you will have the risk of instability. So P2 should be well beyond it to maintain the 20 dB slope at the 0 crossing, but it should be before omega f for it to be of any use, right? If it is beyond omega f, it's not going to attenuate anything at omega f. Okay, so this is how, this is the type 2 PLL, which is the practical phase lock loop that's used everywhere. Okay. No, I mean, yeah, P2 is one pole. If you want, you can have P2 and P3 and so on. No, that's you don't want that, right? Normally, it can be. I think it won't affect it, but normally you wouldn't have that. Not imaginary pole. You mean a second order system? So you mean really two poles, or a complex pole? Yeah, then I can have a complex pole pair P2 and P3. Yeah, that's possible. I don't see the advantage of that though. I think. No, why? Not necessarily, right? No, that means that you have two poles, right? Yeah, whatever. I mean, you can have two poles. Yeah, that's right. So anyway, in practice, the implementation of second order poles is a little more difficult because we do all of this with passive stuff. There is a very simple implementation of this, which can combine with the phase detector that we discussed the other day, which will give us the charge pump and the filter. Okay. So we'll discuss that next class, next week.